No class. Okay, so sorry again about my internet. I've requested a hotspot, so hopefully I'll get that soon and this will not be an issue in the future. But we were cut off again. We were talking about double slit diffraction, and we wrote down that equation where this tells us where, like the angles, if we project this light onto a screen, is giving us the angles where constructive and destructive interference will occur. Beyond that, we have single slit diffraction. So if you shine light through a single slit, the idea is that we treat every point in that opening as a source of spherical waves, and then they're going to interfere on the screen. And this equation gives us the location of the dark fringes, where we get destructive interference. So in that equation, W is the width of the slit, lambda is, of course, the wavelength of light, and M is the order of the dark fringe. Now, beneath that, a very important case, it's very similar to a single slit diffraction, except instead of like a rectangular slit, we have a circular aperture, which it's important because all the light that we see basically goes through a circular aperture, your pupil. And so you will get this interference pattern for everything you see, essentially. But also, optical instruments tend to be circular, like microscopes, telescopes. Very important example. And the idea is, so you look at two objects, or say you look at a single object going through a circular aperture. So let's look at what the intensity of the light would look like. So like here's light passing through an opening, and you get a pattern that looks something like this, where there's areas where you have destructive interference. And that theta, that's the angle to like the first point where we get destructive interference. Now, say we have two objects. So we have light from two objects passing through a circular aperture, and we're going to get two diffraction patterns. I should have used different colors, but you get the idea. These overlap so much that, can you actually distinguish these as two separate objects? And in this case, probably not. Because, you just see this combination here, where if you spread the objects apart farther, then, these patterns would be farther apart, and you could actually, so like if you have two objects farther apart, you might get a pattern like this, where there'll be a little bit of overlap, but like in this case, you can tell that there are two distinct objects. In this case, probably not. And you have like a numerical way to determine if you can tell if you're looking at two objects or not. There's the Rayleigh Criteria, where the central bright fringe just overlaps the first. So if we put these a little bit closer together, so that this first minimum, if we shift that over, so that's right up to lines up with the central bright fringe, then we say, yeah, we can resolve those as two separate objects. And obviously, if they get farther apart, then it's easier to distinguish them. But, so in this equation, this 1.22, it's actually a fairly complicated thing to work out, light passing through a circular aperture, but works out to be that number. Lambda is wavelength, and d is the diameter of the opening. And so another way, if you have a larger diameter, that'll make it easier to resolve things. Now, if you go out at night and look at the stars, you know, a lot of the stars you look at, maybe even about half of them, are actually double star systems. They're binary systems, two stars orbiting around each other. But you usually cannot tell just from looking at them. Almost never you'll actually be able to tell. But with a telescope, you know, what looks like one star to your eye, when you look at it through a telescope, you can see two distinct objects. And you know, bigger the telescope, the easier it is to resolve things. And finally, we have the diffraction grading. And yeah, that's kind of like a double slit experiment, except instead of just two slits, you might have, you know, like 1,000 or 5,000 equally spaced slits. And so you shine light through, and very, very similar equation here. Sine of theta is m lambda over d. But, yeah, there's a nice picture in here, actually. Just get the book to show you the picture. There are some differences between single slit and double slit experiments. Yeah, here's like the... So, let me hold this up. Yeah, the top one is a diffraction grading. And the bottom one is a double slit experiment. And the main difference is that for a diffraction grading, you get more well-defined. There are more localized bright fringes, followed by basically dark fringes in between. But if you look, you can actually see little bumps in there. These are called the principal maxima. But you can get these other smaller order effects, which we're not going to concern ourselves with. Okay. So that's a diffraction grading. This gives you the angle to the principal bright fringes. And D in this case is the spacing between the slits. So you could have like a 1 centimeter object. It might have 100 or even 1,000 spacings in between the slits. So now with the background out of the way, let's do all of the suggested problems. And now then we'll call it a day. So there's 6 problems in total. 4 of them involving the double slit experiment. So first one, we have monochromatic green light with a wavelength of 554 nanometers, illuminates a parallel double slit. So the usual setup. The distance between the slits is 7.7 micrometers. Calculate the angular deviation of the third order bright fringe. So we have m equals 3. So it's a bright fringe. That would be constructive interference. So this will be just a simple calculation then. Sine of theta, this is what we're trying to find, that would be 3 lambda. And all we want is theta. So, actually I forgot an equation here. Yeah, we also, I forgot to write it down. Wish I could just shift everything down. I'll write it here. We also had this equation, where delta is the path length difference. But, yeah, for this problem, we just want to find theta. Oh wait, I wrote down, yeah, the units are not making any sense here. Sorry, I wrote down the wrong equation entirely. Okay, so yeah, the units weren't making sense. Sine of theta has to be dimensionless. Forgot to divide by d. So here, we have sine of theta, 3 lambda divided by d. So let's plug this in. This will be interesting with the units. We have 3. Lambda is 554. Let's convert to meters. So we divide by 10 to the 9. And d is 7.7 micrometers. So yeah, now our units are canceling out. 10 to the 6 over 10 to the 9. That's 1,000 on the bottom. So we have 3 times 554 divided by 7,700. Dimensionless number. So I have like 1,600 divided by 7,700, but let's see. So I'm getting 0.216. So if we take the inverse sine, should be around 20 degrees or somewhere around there. Just you always want to check the, oh, that was a bit off, 12.5 degrees. All right, and then I'm going to check the answer key as well. Seem to be missing that page for some reason. Let's see. Yeah, 12.5 degrees. Okay, so that's problem 1 for the suggested problems. I should not have erased that equation. Well, that's fine. So let's look at problem 2. A double slit experiment is performed with blue-green light of wavelength 512 nanometers. The slits are 1.2 millimeters apart. And the screen is 5.4 meters from the slits. So how far apart are the bright fringes as seen on the screen? Should have probably worded that a little differently, but let's look at, like, here, let's do this. This is, well, yeah, that's y equals 0. Yeah, that's the m equals 0 bright. Then we have the m equals 0 dark. And then m equals 1 bright. So let's find the angle to the first, like, we know theta equals 0 will point to the first bright fringe. Let's find the angle to the next, the m equals 1 bright fringe. And we want to find the actual distance here. Now again, we have this kind of 2 ways we can go about this. But if it's a small angle, then sine and tangent are essentially equal to each other. So now that only applies if the angle is small. But if you just use the Pythagoras Theorem, let's say that's the hypotenuse. And if y is small, compared to the length, which usually it will be, basically if we ignore that, we get h equals L. The hypotenuse and that perpendicular side are essentially equal to each other. Like if this is 5.4 meters, if y is a couple of centimeters, there's essentially no significant difference between those two distances. And so we can make that small angle approximation. If the angle is greater than that, though, well, it's hard to say what the cutoff is, but if you have a large angle, then obviously that would not be the case. But basically we want to find y. So first, let's do sine of theta. So we're looking at the first bright fringe, so it's constructive interference. So we just have lambda over d. So it'll be 512 nanometers. So it'll be over 10 to the 9th. And then we divide by 1.2 millimeters. So let's clean this up a little bit. So if we divide this by 100, we have 5.12 times 10 to the 5th, and then divided by 10 to the 4th, or by 10 to the 9, that leaves 10 to the minus 4. So this is clearly a small angle. If we take the inverse sine, we're going to get a very, very small angle here. So let's not even bother with that. We can say sine of theta is equal to y over L. So y is equal to, here's sine of theta, and then let's multiply by 5.4 meters. So I'm going to multiply 5.12 times 5.4 and divide by 1.2. So this is 23.04. Let's just say 23 times 10 to the minus 4 meters. Or 2.3 millimeters. So remember when I said if y is equal to a centimeter or something, it's completely insignificant. Well, it's even smaller than that. So yeah, these bright fringes are very closely spaced together. So this problem might not have been worded too great, because it's just how far apart are the bright fringes? Well, it's not exactly linear. The spacing isn't going to be linear because there's a sine function involved. But on this scale, the points are so closely spaced together that by the time you get a significant angle where the distance might differ from what you were looking at previously, you're not going to see anything anyways because the intensity of the light drops off. So, yeah, the 2.3 between m equals 0 and m equals 1, you'd essentially get the same thing from m equals 1 to m equals 2. All right, so let's move on to the next one. I might actually leave this picture up. We're still doing a double slit experiment. Let's read the problem. Okay, so a double slit is illuminated with monochromatic light, wavelength 611 nanometers. So again, monochromatic, mono meaning one, so it's just one color, one wavelength. M equals 0 and m equals 1 bright fringes are separated by 1.8 centimeters. So kind of similar to the last one. M equals 0, m equals 1. We're talking about bright fringes. And that's on a screen located 3.5 meters from the double slit. What is the separation between the slits? Okay, so well, we know theta is 0 for the m equals 0 bright fringe. So let's plug in sine of theta equals lambda over d. So that would be the angle of the first bright fringe. The m equals 1 bright fringe, not the central one. So, we're trying to find d. Never mind, we can't just plug that in. And I strongly suspect we're going to be able to use sine of theta is equal to y over L just based on the dimensions again. You know, this is 1.8 centimeters. That's 3.5 meters. Yeah, let's actually do this. Let's find the hypotenuse. So I'm going to plug in the numbers. Let's convert everything to centimeters. So we have 350 centimeters squared. So I neglected the unit. Everything's going to be in centimeters, so it'll cancel out. So let's see, 350 squared. It's 122,500. And 1.8 squared is 3. So you can see why that y is so insignificant. I'm going to take the square root of 122,503, and we're essentially going to get 3.5, or 350 centimeters. I'm getting 350.004. So, in this case, it is very clear that sine of theta equals y over L. I mean, we would have to have an extremely precise calculation to even notice, or measurements to even be able to notice the difference. So now let's solve this for d. So d is equal to, just putting d over here, L over here, so lambda L, and then we divide by y. So let's do this. Lambda is 1.8 centimeters. Let's see. Yeah, we've got all different units here. So probably best just to, let's convert everything to meters and get an exponent to see what prefix to use. L is 3.5 meters. And then y is wait, I think I did, yeah. Plugged in the wrong thing initially. Lambda is 611 nanometers. And then L is 3.5 meters. Y is 1.8 centimeters. So our units here are meters. So let's do this. 6.11 times 3.5 divided by 1.8. So what I did is I took 100 out of here. So this would be times 10 to the 4th over 10 to the 9th. So yeah, I did 6.11 times 100 and then times 100 here. That's 10 to the 4th. Yeah, it looks like maybe micrometers are the way to go here. So let's do this. So we have 6.11 times 3.5 divided by 1.8. So I'm getting 11.9 times 10 to the minus 5. So, that'd be 119 micrometers. I think I forgot to check the enter key for the last one. Oh, I did 0.19 millimeters. Oh, I think that might have been a typo that I wrote down. I'm going to make a note to check this one. I think I just wrote it down wrong. The notes, because I'm getting 119. The last one I just wrote 19. So I think I'll just have to double check that. But, yeah, that's a case where that sine of theta equals y over L is very clearly valid. Yeah, we'd have to go to like 6 significant figures to even notice the slightest difference at all. All right, so one more. This one has a picture, which I'll hold up to the screen. It's the same kind of thing we've been doing, but just a little different perspective. So now it's like picture yourself looking at the screen, and this is what you see. So again, this is a computer drawing, so it's much more, nice rectangles, and in reality, we know that the colors would blend a little better and not form these perfect rectangular objects. But yeah, the thing is, I can't draw it on the screen because the whole thing is black, and then there's light of various intensities. So just remember that picture or look at the suggested problems. But light is incident on 2 slits that are separated by 0.2 millimeters. So the figure shows the interference pattern on a screen that is 1 meter away. So we want to determine the wavelength of the light. And so let's go back to the picture. So we've got these bright fringes. This is m equals 0 bright fringe. That's m equals 1, m equals 2. So we're given the distance to the m equals 3 bright fringe. So from this picture, for the m equals 3 bright fringe, y is 7.5 millimeters. Again, compare that, 7.5 to 1,000. So this is 7.5, that's 1,000. H is basically going to be 1,000 as well. So let's just jump right to it. Sine of theta is y over L. And that would be equal, we're looking at the bright fringes, so that's m equals 3, and then lambda over d. And we want to solve for lambda. So lambda is y d over 3L. All right, so y is 7.5 millimeters. Let's see. Let's leave it. Oh, wait, no, we want to convert to meters. Because then we're given d is also millimeters. So let's convert that to meters. On the bottom, 3L is just 3 meters. But we know light, we typically express that in nanometers. So we have 10 to the 9 nanometers. in 1 meter. So now we have our answer in nanometers. So we have 7.5 times 0.2 divided by 3. We can actually do that without a calculator because 0.2 is 1/5. 1/5 of 7.5 is 1.5. And if we divide by 3, we get 0.5. Just from those three numbers. And then times 10 to the third. So what I'm getting here is 500 nanometers. And that's what I had in the notes as well. Okay, so that's a double slit experiment. And I kind of realized after doing all those, there was nothing involving a dark fringe. So I'd recommend just going in the book and picking one where they ask a question about the dark fringe. No real difference. You just have m plus a half instead of m. But essentially, it's the same thing. So now there's two questions on just diffraction in general. I mean, really, we're talking about diffraction, single slit, double slit, diffraction grading, which could have hundreds of them. Just kind of the details will significantly different. But, so you get diffraction then. So, light shines through a single slit whose width is 5.6 times 10 to the minus 4 meters. A diffraction pattern is formed on a flat screen located 4 meters away. The distance between the middle of the central bright fringe and the first dark fringe (3.5 millimeters). So what is the wavelength of the light? So again, it's between the central bright fringe and the first dark fringe. So m would equal 1. Okay, so for a single slit, this gives us the angle to the first dark fringe. So sine of theta would just be lambda over W in this case. And let's draw it. So we have this angle to the first dark fringe here. So L is 4 meters. And D 3.5. Yeah, that's the distance between the middle of the central bright fringe and the dark fringe. So just like before, we can say that sine of theta, well in this case, this is D, and that's L. Again, 4 meters compared to 3.5 millimeters. Sine and tangent are essentially the same thing. So let's solve for lambda. So we have 5.6 times 10 to the minus 4 meters. Let's convert this to meters as well. We divide by L, which is 4 meters. And because it's light, we know we're going to want to convert to nanometers. So we have 5.6 times 3.5 divided by 4 times 100. So 5.6, 3.5, and 4. Here we have, on the bottom, we have 10 to the 7. So 10 to the 9 over 10 to the 7 is 100. So it's Just plug that in. So I'm getting 490 nanometers. And let me check. So I got the answer key as well. Okay. So one more problem. I think this one involves a diffraction grading. The light shining on a diffraction grating has a wavelength (495 nanometers). The grating produces a second-order bright fringe. So we have our diffraction grating here. And just look at so whose position is defined by an angle of 9.34 degrees. So how many lines, this is for m equals 2. So let's see, second order bright fringe, whose position is defined by that angle. So the question is, how many lines per centimeter does the grating have? So here, sine of theta, we want to find d. Well, okay, wait, d is the spacing between them. Okay, so let's find d. That's a spacing between the slits, but then they want to know how many lines per centimeter. So let's find d first. Okay, so sine of theta would be 2 lambda over d. So d is equal to 2 lambda. Say 495 would be what, 990 if we multiply it by 2. Yeah, then we'll divide, let's just keep it in nanometers. Divided by the sine 9.34 degrees. Okay, so we'll get probably micrometers out of this, but I'm going to do 990 divided by sine of 9.34. Yeah, I'm getting 6,100. Which would be 6.1 micrometers. So that's the spacing between the slits, but that's not really what the question is asking. It's saying how many lines per centimeter does the grating have? So if we have one set, we can say that the number of lines, I'll just write that down. The number of lines times the spacing between them would be equal to the length of the whole thing. And again, maybe a tiny bit off. Like if you have, say, an object like this, if you have, say, 2 lines, that breaks it up into 3 pieces, not just 2. Who cares? We're dealing with large numbers here. That won't make a difference. So the number of lines times the spacing between them would be the length of the whole thing. So let's solve for n. That would be the length of the whole thing. What the lines per centimeter? So let's say we have a 1 centimeter area, or length, divided by 6.1. Here, let's convert it. Let's do this. 1 centimeter. So we can say 1 meter over 100. That's L. and then divided by D, which is 6.1 micrometers. So we put 10 to the 6 on top. So this is 10 to the 6 over 10 to the 4th. Sorry, it's 10 to the 6 over 100. That's 10 to the 4. So I'm taking 10,000 divided by 6.1, and I'm getting 1,640. So that's the number of lines per centimeter. So we set L to be 1 centimeter, found the number of lines we would get on that section of the diffraction grading. Okay, so that's diffraction, and yeah, just one more topic to cover, and that'll be thin films. All right, so that's it for now.